Okay, so that takes care of pressure and volume. What about temperature? That's the next big thing that we talk about. If you're heating something up, how's that going to affect things? Well, in this case, we're going to assume that the pressure stays the same, and we're going to see what happens to the volume when the temperature is increased. Well, we'll think about that as well. If your temperature is an indication of your speed of the molecules, if you increase the temperature, then the things are going faster. Well, if they're going faster, they're going to bang up against the walls a little bit harder, and if the walls can move, then they will, and things will expand. And let's think about it using, again, our buddy Scuba Steve. So we put some more gas inside this container, and it starts bouncing around, and it is pretty much at room temperature. So, in this case, what we're going to do is keep the pressure held constant. And we're going to see what happens when you increase the temperature. And there goes Scuba Steve, he's getting pushed backwards. The molecules are going faster, and it pushed them right off the screen. If we start to shrink it down, or start to decrease the temperature, then the volume is going to start to decrease as well. And this is what happens if you have a balloon and you stick it in the freezer, it gets all shriveled up. If you heat it up, it expands quite a bit. And there's plenty of things on YouTube where you have a balloon and you pour liquid nitrogen on it and the balloon just totally turns into a raisin. Pretty remarkable stuff. You should take a look at that. But that is how the volume changes when you change the temperature. And again, it pretty much makes sense as you're going through it. And that's the setup right here. In this case, it's a straight line on the graph itself. You can see how it just flows its way all the way up. And if you take it all the way back down, you come to something called absolute zero, which is negative 273.15 degrees Celsius. We'll get into that in a second. But you have that arrangement. And the math formula for this is a little different. The first one was P1V1 equals P2V2. And in that case, when one went up, the other went down. This tends to confuse people, but now we're dealing with the fractions. V1 over T1 equals V2 over T2. People think if you're dealing with fractions that things are going to be in backwards. If one goes up, the other goes down. But that's not really the case. And think about it when you reduce a fraction yourself. If you have a fraction of 4 over 8, you reduce it down to be 1 over 2. So what did you do? Well, you took the bottom one and you dropped it down by a value of 4. So you had to do the same thing with the top. You had to drop it down by a value of 4. So if the one on the bottom went down by 4, the one on the top has to go down by 4 to keep it equals. So in this case, if the temperature goes from one level and it drops down to this new level, then the volume is going to do the same thing. It's really pretty logical. It just looks weird when you see the fractions. Don't let that throw you off. So let's do a simple problem in this one. The main key that we're going to be dealing with, we're going to get into in a second, but you have to have the temperature in Kelvin, not in degrees Celsius. But that's not that big a deal. But we're going to explain why in this particular instance. So right now you have got a gas sample at 40 degrees Celsius, and it's taking up 2.32 liters, a little more than a 2-liter bottle. If you increase the temperature to 75 degrees, what's the volume going to do? Well, right off the bat, you know the volume's got to go up. And if you just use the Celsius, you're going to think that the volume is going to be essentially doubled. But it won't. We have to go down and use Kelvin. And Kelvin is 273 degrees higher than Celsius. Actually, it's 273.15, but all the problems in the book just keep it at 273. We'll keep it simple that way as well. So when you've got these values, the 40 degrees Celsius, the 75 degrees Celsius, you need to add 273 to each of them in order to get the correct values. And what that means is you don't have quite as drastic an increase. It goes from 313 to 348. Yes, it's still going up the 25 degrees, but it's not, 35 degrees, but it's not quite as drastic. It's not being doubled, it's only going up by about 10%. So that's going to make quite a big difference. It will expand, it just won't necessarily expand the way you might think it will. So again, You set up V1 over T1 equals V2 over T2. In this case, we have an increase in temperature. So I multiply both sides by T2, bring it up there. V2 is going to be V1 T2 divided by T1. Punch in the values. 348 is the, oops, wrong thing, excuse me. 348 is T2, what the temperature went up to. 313 is what it used to be. Temperature goes up, you see 348 over 313, greater than 1, it's a larger value. Multiply that by the 232, you get 2.58 liters. Goes up just like it should. And just think of the image. You have a temperature increase of a balloon, it's going to expand, and you're going to see that increase as you go along. If you want to flip it around the other way, you can solve for the temperature as well. Using the exact same values, you see how you get the new temperature. And this is, again, just how things are set up in the book. And you can work through a couple of problems just to make sure you're comfortable with this. The last thing to talk about is very similar to what we just talked about. This is Gay-Lussac's law. In this case, pressure and temperature are directly proportional. In this case, as the temperature goes up, so does the pressure, if you keep, the other stuff the same. So let's reset Scuba Steve again. Oops. I'm sorry about that. I didn't clear that. All right. All right, let's reset him. Get the gas back into the container. And in this case, what we're going to do is Scuba Steve isn't going to go anywhere. He's just going to hold steady and keep this box the same size. We're going to keep the volume the same. Now, this usually tends to make the most sense. If I increase the temperature, the gas molecules start going faster and faster. They start hitting the wall harder and harder, which means the pressure has to go up. If I drop the temperature, they slow down. They don't hit the wall as hard. Scuba Steve doesn't have to work as hard. You see him standing up and relaxing. Pressure goes back down. And the math for this is really the same as the math for Charles's law. It's just instead of a P1, it's a P1 over T1 equals P2 over T2 instead of V1 over T1 equaling V2 over T2. So all of this is essentially the same setup. So let's look at this. We've got pressure in a tank, a solid tank. It's not going to change. I usually say a rigid tank or a rigid vessel, something like that. 3.2 atmospheres at 22 Celsius. Raised up the temperature, almost tripled it, but only in Celsius. We still need to change it back to Kelvin. How does it affect the pressure? Well, you know the pressure is going to go up. Let's just see how much. And you see the same setup that we did for Charles's law. First thing I did is I had to add 273, so I'm at 295 where it's at 22, and my temperature rose to 333. Again, jumped up quite a bit, but not quite as drastically as we thought, only about 10%. I had 3.2 atmospheres. That's my P1. T2 over T1. Punch in the numbers, and it goes up by 3.6. And that is how you set things up for Gay-Lussac's law. What we're going to be doing next is we're going to combine these things together and give you a gas law that's really going to cover everything. But again, if you want to just do some practice, these are the problems for Gay-Lussac's law. You can work these out and make sure that you're comfortable with this math as well. But really just keep an idea of what's going on. Keep an eye on Scuba Steve. It's the phet.colorado.edu. And Scuba Steve is under gas properties.